The Mars Opportunity rover launched from Cape Canaveral on a Delta II rocket in July of 2003. It landed on Mars in Meridiana, Lanham, in January of 2004. Opportunity, with a similar rover named Spirit, carried out its mission of mapping and imaging the Martian landscape. Opportunity was solar-powered and operated for 14 years. Dust storms are common on Mars, and these reduce available solar energy. Opportunity would hibernate during these regional dust storms. In June of 2018, Mars was hit with a planetary dust storm. There is nothing on Earth like this. These storms cover the entire planet and can last for weeks. The wind speed is not really a problem. The highest recorded wind speed on Mars is only 100 kilometers per hour. And since the air on Mars is so thin, you would barely feel this wind. The problem is, dust on Mars has an electrostatic charge and sticks to almost any surface. When these storms hit and the entire planet becomes shrouded in dust, solar panels get coated in a thick layer and cannot produce any power. Opportunity did not have a nuclear power cell, and the last signal from Opportunity came on 12 June 2018. The rover went into hibernation mode at that time and never woke up. A human habitat on Mars that was dependent only on solar energy would have to go to battery power and try to last through the storm. Battery power is finite, and without power, humans cannot survive in space. I would like to take a moment to thank all of those who have been supporting the Academy. We appreciate each and every one of you. All of us dream of having a bright future in the space industry. The reasons will be as individual as we are, but one of the most common is to improve the lives of our fellow humans. When you want to improve life for all humanity and believe it is possible to do so, you might be called a humanist. One humanist we are all familiar with was Nikola Tesla. Tesla dreamed of beaming electrical power to all of humanity. He built a massive transmitting tower for this purpose. This was called the Wardenclyffe Tower. It was built in 1902 and was meant to transmit messages, images, and power wirelessly. Tesla had proven that this concept was viable in earlier studies. He had shown that he could power fluorescent lights at a distance. But Tesla made the mistake of wanting to make this power available to everyone. He thought it could be a free public utility service. This did not go over well with those funding his research. Their goal was the accumulation of wealth, and they pulled his funding and shut down the project. The massive tower was demolished, and now the only thing left standing is this building. But the dream of efficiently transmitting power has not died. Several companies have talked about using solar-powered satellites to beam concentrated energy from the sun down to the Earth. Let's look at the feasibility of this idea. A power satellite for Earth would probably be in a geosynchronous orbit. Geosynchronous orbits are about 35,000 kilometers from the Earth. This allows power to be sent down to a ground station, but that limits the usefulness of this concept, as there are very limited orbital slots for geosynchronous satellites. At any non-geosynchronous orbit, an energy beam transmitted from the satellite would be part-time and have to be constantly adjusted to stay on target with the receiver. We also have to consider what type of beam we would use. Non-coherent or regular light would not work at all for obvious reasons. We would therefore have to use coherent light. That means lasers and masers. Visible light lasers, while excellent in space, would quickly dissipate in the atmosphere, as the photon's energy would be absorbed by the atoms in the air. When you see a laser beam, it's losing energy. Visible light is from 380 to 700 nanometers. We should then try to use non-visible light. Ultraviolet won't work because it's absorbed by ozone in the upper atmosphere. But infrared might be a good choice. Some wavelengths of infrared light travel easily through the Earth's atmosphere. These are called infrared windows. These would include J-band at 1,100 to 1,400 nanometers, H-band at 1,500 to 1,800 nanometers, and K-band at 2,000 to 2,400 nanometers. These wavelengths would make it through the atmosphere, but there would be a problem of beam divergence. Beam divergence is the widening area of a laser pulse over distance. We can calculate beam divergence of a laser using Gaussian beam calculations. We start with this equation, which will give us beam divergence in radians, by dividing the wavelength by pi times the laser's aperture. If we go with a wavelength of 1,100 nanometers, that's 0.00000011 meters, and an aperture of 10 millimeters or 0.01 meters, the aperture can be considered the last opening the laser passes through. This can be a lens or shutter. If we multiply the aperture times pi, we get 0.03142. When we divide the wavelength by this number, we get 0.000035 radians. If we then multiply pi by the beam divergence in radians times the distance squared, this will give you the size of the projected beam. The distance is 35,000 kilometers, which is 35 million meters. We multiply beam divergence times distance and get 1,225.5. That gives us 1,501,833 square meters. This is a big area, and we would need an antenna this size to get all the power. That's a dish more than 2.45 kilometers across. The largest dish on Earth is in China, and is only half a kilometer across. And that brings us to another problem. The power satellite would have solar panels. The solar flux at the orbit of the Earth is 1,373 watts per square meter. The most efficient experimental solar panels reasonably available today are about 30% efficient. Let's go with that number. And let's add Stirling engines. These engines will produce power as long as there is a temperature differential between the two ends. If you are not familiar with Stirling engines, please review this lesson on Stirling engine technology. If the Stirling engines can add another 20% efficiency, we'll be at 50%. That would mean 686.5 watts of energy produced per square meter. This is a very optimistic estimate. Reality would probably be close to 1/3. If we have a very large solar panel, 100 meters by 100 meters, we would have 10,000 square meters total. This would give us 6,865,000 watts or 6.87 megawatts. And now we have to turn this into an infrared laser beam. Lasers are only about 20% efficient in turning power into laser light. That gives us 1,373,000 watts of laser energy. This energy comes down to the Earth and is captured in our almost 2.5 kilometer diameter dish. Let's assume the dish is 100% efficient at collecting this energy. We then need to convert back from infrared energy to electric power. At the best, we could expect an efficiency of maybe 30%. 30% of 1.37 megawatts is 411,900 watts. We have launched a massive satellite into orbit, equipped with an advanced laser. Assumed no energy loss in the atmosphere, though there would be some, and built this massive collection dish to produce 411,900 watts of energy. What if we just put regular solar panels at 20% efficiency in the area of this dish? A 2,500 meter diameter dish would have an area of 1,562,500 square meters. About 1,000 watts per square meter of solar energy makes it through the atmosphere to the surface. At 20% efficiency, that gives us 312,500,000 watts of energy. So we can put up a big satellite to get less than half a megawatt, or just use solar energy on Earth to get over 300 megawatts. Does that make this concept useless everywhere? No, it doesn't. Any colony on the moon, if they are not in the permanent polar shadow, will experience an almost 15-day period of darkness. We could call this night, but for clarity, I like to call it darkloon. Also because it sounds cool. The sunlit period is dayloon. During this period of darkness, power will be a problem. It is possible to put something into orbit, on the far side or near side of the moon, and have it stay in a stable position relative to the moon. On the near side, this is called Lagrange point 1 or L1. This is an island of gravitational stability between two orbiting bodies. There are 5 Lagrange points around every orbiting body. Lagrange 1 is between the two orbiting bodies. Lagrange 2 is on the far side of the smaller orbiting body. Lagrange 3 is on the opposite side of the larger orbiting body. Lagrange 4 and 5 are 60 degrees behind and ahead of the larger body. These points exist around all moons and planets. Between the Earth and Moon, you can see them here, and here between the Earth and Sun. A halo orbit is a little different. This is where you place a ship or satellite into orbit around a Lagrange point. We could do this at L1 between the Earth and Moon, or L2, just past the orbit of the Moon. L2 is where the Chinese satellite Keqiao is located. These are called halo orbits because the satellite transcribes a circle above or below the orbiting body. The Chinese did this to communicate with their lander and rover on the far side by using the satellite as a relay station. There could be another use for these orbits. If we put a power satellite here, it would be about 58,000 kilometers from the Moon. This power satellite could project a power beam. Probably microwave would be best, down to the Moon. Converting electrical energy into microwaves is about 90% efficient, and we are very good at focusing microwaves into a narrow beam. The Moon also has no effective atmosphere to attenuate power. So a beam projected over a base could provide a continuous power source, so that any device with a receiving antenna could absorb power. If the solar panels produce 6.8 megawatts, as before, we could project a beam of a little more than 6 megawatts. This beam would spread out from divergence and end up covering an area of perhaps 2,000 square kilometers. If the conversion back was also 90%, which it can be for microwaves, we are looking at almost 3 kilowatts per square meter. That means that any rover, habitat, or astronaut with a 1-meter antenna could receive a continuous 3 kilowatts of power. This could be critical for long-term survival. No matter how good your energy storage system is, you must have an independent backup source of power. What other uses are there for projected energy beams? There was once a rocket planned to launch from Earth using beamed microwave energy to heat propellant in a rocket. It was hoped that this would be more efficient than chemical engines. They could use pure hydrogen propellant, which would have the highest specific impulse in a thermal rocket. The rocket would be absorbing the energy over its skin and transferring this to the propellant. But as the rocket climbed, the divergence of the microwave beam would rapidly get too large, and the energy per square meter incident on the rocket would get weak. This rocket would never get to orbit. And it turns out that the problem with chemical rocket efficiency is the engine components cannot take a higher temperature. We have not maximized the efficiency of chemical rocket engines yet, until we develop alloys that can survive the temperatures produced in what's called stoichiometric combustion. All modern rockets are purposely down-tuned, so they can survive the temperatures and pressures produced. Once you reach the temperature limit of your combustion chamber alloy and cooling system, you're stuck. The only other way to improve performance is to stuff more propellant into the combustion chamber. The Raptor rocket is so remarkable because SpaceX was able to develop alloys that can resist much higher pressures than other rocket engines. This allows a much higher thrust-to-mass ratio and reduces residence time, which is how long propellant must stay in the combustion chamber to absorb thermal energy. Thermal energy is just kinetic motion of molecules. As these molecules exit the throat of the engine, this kinetic energy is converted into ejection velocity, which gives us thrust. What else could we do with energy beams? Let's go back to Mercury. To get off the surface of Mercury and into a stable orbit, we will need a lot of thrust. But unlike on Earth, we don't have to worry about aerodynamics. We could build a 10-meter by 10-meter solar panel. The power flux on Mercury is 8,581 watts per square meter. With an efficiency of 50% using solar and Stirling technology, we could get over 400 kilowatts of power. We could also use ground-based microwave projectors to help us get to orbit. Putting our ship on an electromagnetic mass driver is also possible. If we install a microwave electrothermal rocket engine and use hydrogen propellant, we could get into orbit with only about 20% the propellant we would need for chemical engines. And all of this is reusable. Coming back to land, we could use projected power to boost the thrust during the landing burn. Hydrogen is an excellent propellant for rockets. For thermal engines, nothing is better. There was some concern, after the lesson on colonizing Mercury, that electrolyzed water would always have to be used for propellant, and we would therefore deplete the water available in the poles of Mercury, dooming our colony long term. There is another solution to getting hydrogen on Mercury long term. I think in the future, water on Mercury will be kept in the base and recycled, and we will use another source for hydrogen. The solar wind is composed of 95% hydrogen and 4% helium, including helium-3, with less than 1% nitrogen, carbon, oxygen, and other elements. One thing we could do in the future is put a large satellite in orbit around the Sun, at an orbit, let's say, the same as that of the Parker Solar Probe, since we know that we can design satellites to survive this. The Parker Solar Probe came within 10.4 million kilometers from the Sun. That is only 0.07 AU. Solar power at this distance is over 200 times that at the Earth's orbit. This satellite would look like a giant radar dish. The dish would be made of heat-resistant solar panels. The electrical energy produced would be used to power superconducting magnets. These magnets would create a funnel-shaped magnetic field, much larger than the physical size of the dish itself. These magnetic field lines would focus the solar wind into the funnel, where they would be redirected out the back of the satellite and through these focusing rings. These rings are also superconducting coils, powered by cables from the main power collector. The purpose of these rings is to create a laminar flow of protons. A laminar flow is when you get almost all of the particles in a fluid to flow in the same direction in layers. This is used in water devices to make laser-like projections of fluid. This creates a beam with very little divergence. The direction of this beam could be changed by shifting these focusing rings. The solar wind would push the satellite back like a sail, but the beam focused out the back could be accelerated by the coils to offset this pressure. If there were enough of these coils, we would have a laminar proton beam. This beam could travel great distances with very little divergence, and a collecting device could be built in the orbit of Mercury. This device would have a collection of superconducting coils also. These coils would be solar-powered too. Remember that solar power at the orbit of Mercury is over 6 times what it is at the orbit of the Earth. These coils would produce an arresting magnetic field. Electrical energy can be harvested from a charged object moving through a magnetic field. This energy could be fed back into the coils to harvest the protons. Excess energy could be beamed to the city as microwaves. As the protons slowed, electrons could be fed back into the plasma to produce neutral hydrogen and some helium. These resources could be cooled and condensed and placed into storage tanks in orbit. Some of this could be sent down to the surface to be used for propellant. Some could be kept in orbit for refueling. On the surface of Mercury, you don't have to combine oxygen with hydrogen to get off the planet. Just separate the helium-3 from the helium-4. Save the helium-4 to be used in heat pipes, and use the helium-3 in an aneutronic fusion reactor. Cool the reactor with liquid hydrogen, and you've got a fusion thermal rocket. This should give you a specific impulse of at least 2,500, with a lot of thrust. Now you can get into orbit easily, refuel with more hydrogen, and use advanced solar electric or solar thermal propulsion to do a sun flyby, using the sun's gravity and solar power to get you out to Earth orbit efficiently and fast. As you approach Venus and the solar power is waning, fire up your helium-3 fusion thermal engine again to get into orbit around the Earth. You could trade some helium-3 and other materials mined from Mercury for supplies from Earth, or trade carbon for water from the Moon. Then head back home, using a fusion drive to get you to a Venus flyby, then advanced solar propulsion to get you back home, using the fusion drive to land back on Mercury. Mining the solar wind will someday be a very lucrative industry, and I hope I live long enough to see it. Thanks for listening. Please don't forget to like and subscribe, and stay safe at Astra Pro Terra.